Welcome back to the deep dive. Today we are taking a truly foundational look at matter, moving far beyond the sort of fixed limitations of conventional lab X-ray diffraction.
Right, the method most people start with.
Exactly. And we're plunging into the specialized, high-powered tools used to uncover the deepest secrets of crystal structures.
You shared a fantastic and, I have to say, pretty dense source with us, Chapter 13, Other Diffraction Techniques.
It really drives home a critical point in material science, doesn't it? Solving the hardest problems isn't about finding the one best instrument for everything.
No, not at all. It's about selecting the right probe to achieve the maximum contrast for whatever atomic secret you are trying to reveal.
And that is precisely our mission for this deep dive.
It is. We want to guide you through the distinct physical principles, the demanding instrumentation, and the unique applications of three powerhouse techniques.
Neutron diffraction, electron diffraction, and high-energy synchrotron X-rays.
And we're going to follow the chapter structure exactly, focusing on how these specialized probes reveal details that traditional X-rays they just can't resolve.
Things like the precise location of a hydrogen atom.
Or the complex alignment of magnetic moments, yeah.
Okay, so let's unpack this with core concept overview from section 13.1. The fundamental physics that base remains unchanged, right?
Correct. Whether we're using X-rays, neutrons, or electrons, all of these methods rely on the scattering of either electromagnetic radiation or particle waves from atoms.
We're still using the famous Bragg equation and the concept of the structure factor to figure out what the material's made of and where all the atoms sit.
But what defines the differences, and what the chapter stresses right away, is the context of expense and, frankly, access.
Standard X-ray diffraction is pretty common. You can find it in most labs.
It's ubiquitous, yeah. Relatively economical. Electron diffraction, that requires a Transmission Electron Microscope, which is expensive, but you'll still find them in major university or industrial labs.
But if your problem demands neutron beams or, certain high-energy X-rays, you're in a completely different league.
A different lead entirely. You're talking about national and international facilities.
So massive particle accelerators or reactor facilities.
Exactly. These are high-flux experiments needing immense infrastructure. You have to compete for beam time at facilities that can be hundreds of meters long.
And that huge scale difference reflects the difference in how these probes actually interact with matter.
It does. X-rays are electromagnetic radiation, so they scatter off the spatially distributed electron cloud.
Electrons are charged particles, so they also scatter pretty strongly off charges.
Right. But the real structural detective, the one we'll start with, is the neutron.
Ah, the neutron. The subject of our first major segment, section 13.2, neutron diffraction. So, if the neutron is electrically neutral, how does it see anything at all?
That's the key question.
And what makes it so special that scientists will travel across continents just to use a neutron beam?
Well, the neutron, discovered by Sir James Chadwick back in 1932, is, as you said, neutral. Its mass is just slightly heavier than a proton.
And its neutrality is actually its first huge advantage.
It is. It means it can penetrate extremely deep into matter, so you can analyze much larger bulk samples. That's a massive benefit for, say, engineering materials.
But more critically, it interacts with matter in two fundamentally distinct ways that X-rays can't touch.
And here is where that contrast becomes so important. If X-rays scatter off that large, fluffy electron cloud...
What's the neutron's target for crystallography?
It's the tiny, dense atomic nucleus. The nucleus is about 1,000 times smaller than the atom itself. We're talking a scale of just 0.00004 nanometers.
So that interaction with the nucleus is the basis for figuring out the atomic arrangement.
That's right. And the second, equally important interaction is tied to the neutron's own intrinsic magnetic dipole moment.
Which allows it to interact directly with the magnetic moments within the material.
Precisely.
So this unique capability probing both nuclear and magnetic structure at the same time leads us to the four applications the chapter outlines for neutron scattering. Let's really drill down on these.
Okay. The first and most common is what's called erastic nuclear scattering. This is your standard Bragg diffraction used for crystal structure determination.
But because the neutron scatters off the nucleus, its scattering power, what's called the nuclear scattering length, it doesn't depend on the atomic number, zetate, in a simple way.
And that is transformative, especially when you have heavy elements mixed with light ones.
Why is that difference so critical for light elements?
Just think about X-rays for a second. They see electrons. Lead has 82 electrons. Hydrogen only has 1.
Right.
So if you try to find a hydrogen atom in a lead compound with X-rays, The scattering from that single electron is just completely washed out by the 82 electrons from the lead. The hydrogen is basically invisible.
But with neutrons.
With neutrons, the interaction is with the nucleus, and the interaction strength for hydrogen's nucleus is actually comparable to, sometimes even stronger than, heavy elements.
So locating light atoms like hydrogen, oxygen, or deuterium is much, much easier.
Far easier and more accurate, and this is huge for studies of polymers, biomolecules, water molecules, and crystals, or, ceramics where oxygen positions are key.
That sensitivity to light atoms solves a whole class of problems X-rays can't even touch. Okay, the second use takes advantage of that magnetic moment, the elastic magnetic scattering.
This is really the exclusive domain of neutron diffraction. Because neutrons have a magnetic moment, they are the perfect probe for studying the magnetic structure of crystals.
So by measuring how the neutron spin interacts with the magnetic moments of the electrons,
we can determine the precise direction and magnitude of those atomic magnetic moments. This is absolutely essential for studying complex ordering like antiferromagnetism, where neighboring spins are antiparallel. You can literally see the magnetic arrangement.
amazing. The third application moves us from static structure to dynamics. 3. Inelastic neutron scattering. What kind of dynamic properties can we get at here?
Inelastic scattering happens when the neutron actually exchanges energy with the crystal.
And it exchanges that energy with what specifically?
With phonons, which are the quantized lattice vibrations. You can think of them as vibrational waves traveling through the crystal.
And because the energy of thermal neutrons is similar to the energy of these phonons.
The energy exchange is easy to detect. This lets us study the dynamic properties of the lattice, measure how stiff the chemical bonds are, and see subtle phase transitions.
So for example, studying ferroelectric materials near their Curie temperature.
That's a perfect example. You use inelastic neutron scattering to watch the softening of specific vibrational modes that actually drive the transition. It gives you this unique window into the mechanics of how materials behave with temperature.
That's a huge application.
Yeah.
Okay, and finally, the fourth use for isotopic substitution is a powerful strategy because the interaction is nuclear, not electronic.
Absolutely. The neutron scattering power is highly dependent on the isotope.
Meaning elements with the same chemical behavior, but a different number of neutrons.
Have dramatically different scattering factors. This is a complete game changer for biology and polymer science.
You can replace hydrogen with deuterium.
Researchers do it all the time. The scattering factor for deuterium D is vastly different from hydrogen H. So if you strategically place D atoms in a polymer chain or a protein, those parts will stand out dramatically in the diffraction pattern. You create contrast where there was none before.
And you just cannot do that with X-rays or electrons.
Nope, they're completely blind to the number of neutrons in the nucleus.
That is a phenomenal set of capabilities. But none of this happens cheaply. So let's move to section 13.2.1, neutrons, generation, and properties. How do we actually produce a useful beam of these things?
For the kind of flux we need, they're generated either through controlled nuclear fission in reactors or, more and more, through what are called spallation sources.
Spallation sources, what are those?
They're massive facilities. You take high-energy protons, accelerate them, and then slam them into a heavy target material like mercury or lead.
And this collision.
This violent collision causes the target nuclei to spall, which means they just eject a burst of neutrons.
Okay, so once they're generated, these neutrons are incredibly energetic, way too fast for diffraction. The chapter classifies them cold, thermal, fast.
But only the thermal ones are really useful for this.
Why is that?
Because we need their wavelength to be suitable for probing the distances between atoms, which are on the order of, say, 0.1 to 0.3 nanometers.
And if we calculate the de Broglie wavelength for thermal neutrons at room temperature,
their kinetic energy is about 0.025 electron volts, which gives a wavelength of around 0.18 nanometers. That's the sweet spot for Bragg diffraction.
So if the source makes fast, high-energy neutrons, we have to slow them down. This is the concept of thermalization. How does that work?
You can't just filter a fast particle beam. Instead, you slow them down by forcing them to collide over and over again with light atoms in a moderator material, often water, or heavy water, or graphite.
It's like a cue ball hitting billiard balls.
That's a great analogy. The neutron is the cue ball, and with each collision, it transfers energy, slowing down until it reaches thermal equilibrium with the moderator.
Meaning its average kinetic energy is now predictable.
Exactly. It follows the relationship. EMD is approximately frac C2 kb T2. This gives us a useful distribution of wavelengths.
Okay, so once they're thermalized, we still have a range of wavelengths. Section 13.2.2 is about wavelength selection. For precise diffraction, we need a single monochromatic wavelength. How do they do that?
The chapter details 3 main methods, and they're all really clever bits of engineering. The first is time of flight, or TOF.
Time of flight.
If the source is pulsed, like a spallation source, the neutrons all start at the same time but travel at different speeds based on their energy.
So you just measure how long it takes them to get to a detector?
Exactly. You know the distance, you measure the time, you can calculate their velocity, and then their exact wavelength. Timing is everything.
So measuring the speed directly, what about physical selection methods?
The second uses velocity selectors, sometimes called choppers. Imagine a rapidly spinning cylinder with helical channels made of a neutron-absorbing material.
Ah, so only neutrons traveling at one specific speed can make it through the helix without hitting the sides.
Precisely. Any other speed gets absorbed. It physically filters them.
And the third method takes us back to crystal physics.
It does. We use single crystal monochromators. Just like with X-rays, we use a large, perfect, crystal-like copper or germanium to select a single wavelength from the beam via Bragg diffraction.
And that selected beam is what goes on to the sample.
Right. This usually gives the most precise monochromatic beam for high-resolution work.
Okay, now let's talk about the core physics difference in the scattering factors from section 13.2.3. We said that for neutrons, the interaction is with the nucleus, so it's point-like. What does that do to the math?
It simplifies it immensely. For X-rays, the electron cloud is spread out, so the X-ray scattering factor drops off as the scattering angle theta increases. The math has to account for the shape of the cloud.
But for neutrons, the interaction is point-like.
So the scattered intensity is uniform in all directions. That means the nuclear scattering length is constant. It is completely independent of the scattering angle, the theta.
That's a huge simplification.
Yeah.
You don't need all those angular correction terms you have with X-rays.
Precisely. It makes structural calculations much simpler. But the complexity comes from its dependence across the periodic table. As we said, theta dollar does not vary smoothly with atomic number zeal.
You can't just predict it by looking at the periodic table.
Well, not at all. Iron and cobalt, Z equals 26 and 27, have a huge difference in dollars, but their X-ray factors are almost identical. On top of that, dollar can be positive or negative.
What's the physical meaning of a negative dollar value?
A negative dollar just means there's a 180-degree phase shift when the neutron scatters relative to the incident wave.
So when you're calculating the structure factor for a compound with both positive and negative diddle atoms,
those contributions can interfere in unique ways, creating another source of contrast that just isn't there in X-ray studies. This non-smooth, non-monotonic variation is what gives neutrons their power to tell apart chemically similar elements.
okay, that covers the nuclear scattering. We also need to define the magnetic part of the scattering factor.
Right, that's the magnetic scattering length. This
Yeah.
comes from the interaction between the neutron's own spin and the total spin angular momentum of the atom's unpaired electrons.
And unlike the nuclear scattering length, this one does depend on the scattering angle.
It does, because it depends on the magnetic form factor of the electron cloud, which itself is spatially distributed.
So how do researchers use this to figure out complex magnetic ordering?
By analyzing the magnetic contribution to the diffraction pattern, we can actually map the magnetic structure. The key is that magnetic ordering, especially something like antiferromagnetism, often creates a magnetic unit cell that's a multiple of the crystallographic unit cell.
For instance, in an antiferromagnet, if the spins go up, down, the magnetic pattern repeats over twice the distance of the chemical unit cell.
Right. And a larger unit cell in real space means what in reciprocal space?
It means you get new, more closely packed reciprocal lattice points.
Exactly. And those show up as extra diffraction peaks called magnetic superlattice reflections. They're not allowed by the crystal structure alone. They're unique to the magnetic structure.
And that allows for the creation of specialized magnetic space groups.
It does. It's a capability that is just standard for neutrons.
Okay, let's pull all of this together with the amazing practical example from section 13.2.5, the Texfico alloy. This really sets up the need for all 3 of these advanced techniques.
It's the perfect case study. So researchers want to know if their FICO alloy is ordered, meaning Phi atoms on one sublattice, Co on another, or if it's disordered, just a random mix.
If it's ordered, the structure should have superlattice reflections at positions like 100 or 111.
Right. So step 1, you try standard X-ray diffraction, and what does it tell you?
Almost nothing.
Almost nothing. Iron Z26 and cobalt Z27 are neighbors. Their X-ray scattering factors are almost identical.
So when you calculate the expected intensity for those superlattice reflections, it's basically zero.
Right. The diffraction pattern for an ordered feco-alloy looks identical to a disordered one. X-rays fail to see the ordering.
So we turn to the neutron.
We turn to the neutron beam and the difference in their nuclear scattering lengths. Fe has a dollar of $9.54 femtometers, while Co is just 2.49. That's a huge inherent difference.
And when you plug those values into the structure factor equation,
The expected intensity for the superlattice reflections is now large, and sure enough,
the neutron diffraction pattern clearly shows the 100 and 111 superlattice peaks.
clear as day. It's direct, unambiguous evidence of the atomic ordering that X-rays completely missed. It is the clearest example of how choosing the right probe dictates the success of your experiment.
That's a perfect transition. Neutrons solve the problem for bulk materials where elemental contrast or light atoms are the issue. But what if your material is only a few nanometers thick?
Then you have to pivot completely. Away from bulk-penetrating neutral particles to highly charged, surface-sensitive electrons.
Which brings us to Section 2, Electron Diffraction, Section 13.3. Here, the physics is totally dominated by the electron's charge and its incredibly small wavelength.
Right. Section 13.3.1 covers the electron as a particle and a wave. We're talking about charged light particles accelerated by massive voltages up to 400,000 volts.
And the immediate consequence of that high acceleration is that they're moving incredibly fast.
They're approaching the speed of light. At 400 kilovolts, they're at 83% of C. This means we have to use relativistic physics.
The classical de Broglie wavelength formula isn't accurate anymore.
Nope. We use the relativistic expression. And the consequence is a ridiculously short wavelength. For 400 kiloV, lambda is about 1.644 picometers.
1.6 picometers. That's more than 100 times shorter than typical X-ray wavelengths.
And that extremely short wavelength, combined with the electron's charge, fundamentally changes everything about the interaction.
The probability of it interacting with the material is enormous.
Huge. The source says it's about 10,000 times stronger than for X-rays.
Is that difference really that dramatic? And what are the main consequences of such a strong interaction?
It is absolutely that dramatic, and it means two things. First, electrons get absorbed very quickly. This is why electron diffraction must be done using extremely thin samples, just a few hundred nanometers thick.
And second,
the probability of multiple scattering events is basically 100%. The electron doesn't just scatter once, it diffracts, and then that diffracted beam diffracts again off another set of planes.
and that second point means we have to completely change how we analyze the data.
Yes. Since the scattering isn't independent, we can no longer use the simple linear kinematical diffraction theory we use for X-rays. Electron diffraction patterns have to be analyzed using the complex rules of dynamical diffraction theory.
Which is a massive computational hurdle compared to X-ray analysis.
A huge one.
Okay, let's talk about Section 13.3.2, the geometry of electron diffraction. That super short wavelength has a big impact on our visualization tool, the Ewald sphere.
It does. The Ewald sphere's radius is 1 over lambda. Since lambda is in picometers, the radius is massive. For 100 kiloeV electrons, it's about 48,000 inverse nanometers.
So when you plot this sphere in reciprocal space, it's so large it's practically flat.
That's the key image, the flat Ewald sphere.
And what does a flat Ewald sphere mean for Bragg's law?
Well, the Bragg condition says the reciprocal lattice point has to lie exactly on the surface of the sphere. Since the sphere is practically a flat plane, it cuts through and intersects many reciprocal lattice points all at once.
Which is why a typical electron diffraction pattern shows so many more diffracted beams than an X-ray pattern.
Exactly. And there's another consequence of the thin sample. The reciprocal lattice points actually turn into rods.
Right. Why does limiting the crystal's size in one dimension do that in reciprocal space?
It's a direct consequence of the physical limits. For such thin samples, the reciprocal lattice points get elongated into rods that are perpendicular to the sample surface. Diffraction happens whenever our flat Ewald sphere intersects these rods, which again is easy to achieve for many reflections at once.
So we need specialized hardware for this. Section 13.3.3 introduces the Transmission Electron Microscope, or TEM. Describe this column of optics for us.
The TEM operates vertically inside a high vacuum column, and it uses magnetic lenses to control the electron beam.
And it has 4 main sections.
Right. At the top, the electron gun generates and accelerates the beam. Below that, condenser lenses focus the beam onto the sample.
And then the third section has the objective lens, which is the most critical part for imaging and diffraction.
Absolutely. The objective lens focuses the electrons that pass through the sample, and because of the lens geometry, the physical image of the sample, the real space information, is formed in what's called the image plane.
While the diffraction pattern, the reciprocal lattice, is formed simultaneously in the back focal plane.
Correct. And then the final sections, the magnifying and projector lenses, let the operator choose whether to project the real space image or the reciprocal space diffraction pattern onto the detector.
Okay, let's look at the basic observation modes in section 13.3.4. When we project the diffraction pattern, we see these spots, but dynamic scattering can cause issues, especially something called forbidden reflections. Explain that for us.
A forbidden reflection is a position where, based on the crystal's symmetry, the intensity should be 0. For example, in some structures, reflections like zero wounds where L is an odd number should just not exist.
That sometimes they show up.
Sometimes they do because of dynamic scattering.
How does that happen physically?
It's caused by double diffraction. The incoming beam might hit, say, the 110 planes and diffract. That new diffracted beam then acts as a new incident beam and hits a second set of planes, maybe the 111 planes. The resulting beam from that second event might land exactly where the forbidden 001 reflection should be.
So you see intensity at a forbidden spot, but it's from a two-step process.
Exactly. It's a common challenge when you're interpreting electron diffraction data.
That makes the analysis so much trickier. But the TEM is also an amazing imaging tool. Walk us through the three main imaging techniques.
Okay, so the TEM uses an aperture to select which beams contribute to the final image.
First is bright field.
Bright field, BF, is the simplest. You insert an aperture that only lets the unscattered transmitted beam pass through. Crystal defects appear darker against a bright background.
Then there's dark field.
Dark field DF is more specialized. You shift the aperture to select only one specific diffracted beam, say the 111 reflection.
So the image is formed only by electrons that scatter from those 111 planes.
Right, and this is incredibly powerful for visualizing specific defects like stacking faults. Only the part of the crystal that's perfectly oriented to diffract that beam lights up brightly against a dark background.
And the third, and most complex, is high-resolution electron microscopy.
ATRIM, yes. Here we use a large aperture to combine the unscattered beam and multiple diffracted beams together. When these beams recombine, they interfere and create a lattice image.
And you can directly visualize the projected structure of the crystal.
You can literally see the rows of atoms. It's how you can confirm, say, the tetragonal structure of BaTiO3 at the atomic scale.
That direct visualization is incredible.
Mm.
Okay, moving to section 13.3.5, Convergent Beam Electron Diffraction, or CBED. This is another specialized tool that focuses on symmetry. Why is converging the beam so important?
Standard electron diffraction uses a parallel beam, which gives you sharp spots. CBED focuses the incident beam into a cone onto a very small area, often just a few nanometers wide.
And because the beam is a cone, it includes a wide range of incident angles all at once.
Exactly, and that changes the diffraction pattern from sharp spots into circular disks.
Okay, so you get disks instead of spots. What does that tell you?
Each disk contains the full diffraction information for that tiny area. And the critical application of CBED is the unambiguous determination of the crystal's symmetry. By analyzing the symmetry features you see within these disks, the whole pattern symmetry, you can deduce the crystal's point group and, crucially, its exact space group.
This goes beyond just the 2D projection of the symmetry, right?
It does. CBED reveals the three-dimensional symmetry elements, including things like glide planes and screw axes, through the patterns you see inside the disks. It allows crystallographers to unambiguously nail down the 3D space group of a material, which is often impossible with other methods.
That brings us to the end of our electron journey. We've covered neutral particles for bulk and magnetism, and charged particles for nanoscale work. That transitions us beautifully to our third technique. What if you need the bulk penetration of X-rays, but also the kind of elemental contrast neutrons give you?
Well, then you need section 3, synchrotron X-ray sources. This is, as you said earlier, X-rays on steroids.
Exactly. So section 13.4, the principle of synchrotron radiation. We are talking about X-rays generated not by heating a filament, but by accelerating charged particles, usually electrons, moving at relativistic speeds in a circle.
That's the core idea. When these relativistic charged particles are forced to change direction by powerful magnets, they emit intense electromagnetic radiation X-rays tangentially.
Section 13.4.1 details the accelerators. When we say massive facilities, we're talking about rings hundreds of meters in circumference. Walk us through the life of an electron in one of these places.
It's quite a journey. Electrons are generated and shot into a linear accelerator. Then they're boosted to higher energies in a smaller booster ring, and finally injected into the large circular storage ring.
And there they just circle for hours.
For hours, yes, kept in their path by powerful magnets. The total energy and current in that ring dictate the power of the X-ray beam.
Okay, so what are the main advantages compared to a conventional lab source? The chapter lists 4 key properties.
First, and most strikingly, is high-intensity brilliance. Synchrotron radiation is a continuous spectrum, and its power is proportional to the fourth power of the electron energy.
E400 So a small increase in energy gives a huge increase in power.
Enormous. A synchrotron can be 100 million times brighter than a conventional lab source.
100 million. What does that mean practically for a scientist?
It's transformative for time result studies. You can collect a high-quality diffraction pattern in milliseconds.
So you can study crystallization, phase transformations, or chemical reactions as they are
In
happening.
situ, yes. You can also study incredibly small samples or very dilute materials that would be impossible with a lab source.
Okay, the second key property is tunability. This is central to its utility.
Because the radiation is a broad-spectrum white light source, scientists can use crystal monochromators to select a single precise energy or wavelength.
And they can tune that wavelength across a huge spectrum. You're not stuck with the fixed wavelengths like copper K alpha from a traditional source.
Exactly.
Property 3, high polarization.
The X-rays are almost 100% linearly polarized in the plane of the electron orbit. This is crucial for advanced magnetic scattering experiments.
And finally, the modern engineering additions. Insertion devices like wigglers and undulators.
These are sophisticated arrays of magnets installed in the straight sections of the ring. They create an alternating magnetic field that makes the electrons wiggle back and forth.
And all that extra acceleration.
And dramatically enhances the flux and brilliance, basically tailoring the X-ray beam for a specific experiment.
Let's talk about section 13.4.2, the experimental examples. While the high flux is critical, that tunability leads us to the most unique feature, anomalous scattering.
Right. Anomalous or resonant scattering is how we use a synchrotron to mimic the elemental contrast of neutrons, but with an X-ray probe.
So when the X-ray energy is far from the absorption edge of an element, the scattering factor is pretty constant.
It is. But if we tune the X-ray energy precisely near the specific absorption edge, the K or L edge of a target element,
What happens to that scattering factor?
it changes dramatically. When the X-ray energy matches the binding energy of the core electrons, the X-ray wave momentarily excites them. This resonance disrupts the normal scattering, causing the scattering factor to change drastically. The atom scatters anomalously.
And this is the physics that lets us solve the FICO problem with X-rays. Let's close that loop now.
Perfect. We saw that standard X-rays failed because the scattering factors for Fe and Co are almost identical. But with a synchrotron, we can tune the beam right next to the K edge of, say, iron.
And that tuning causes a huge anomalous change in the scattering factor for iron, while cobalt remains relatively unchanged.
Exactly. We induce a massive difference in the scattering contrast where there was none before.
And suddenly, the X-ray structure factor for those superlattice reflections, which was 0 before.
Becomes strongly non-zero and observable. Synchrotron X-rays, by leveraging tunability and anomalous scattering, solve the exact same ordering problem that neutrons solved, but through a totally different electromagnetic route.
That beautifully connects all 3 techniques through one core problem.
It proves that if you can't see it with one probe, you change the physics of the interaction until you can.
Let's wrap up with section 4, a brief look at history and synthesis. The chapter reminds us how long these ideas took to mature.
The history is really fascinating. J.J. Thomson established the electron concept in 1897, but it took decades to confirm its wave nature.
The Nobel Prize for demonstrating electron diffraction was shared by his son, G.P. Thomson and Davison and Germer in 1937.
Right, cementing wave-particle duality.
And the power of neutron diffraction came even later, really requiring the nuclear age.
Correct. That Nobel Prize was awarded much, much later, in 1994, to Clifford Shull and Ernest Wolin for their foundational work back in the 40s and 50s. And the development of synchrotrons is still an ongoing story, with each generation of machine getting more and more powerful.
Okay, let's synthesize these 3 techniques. For the listener trying to decide which tool they might need, what's the clear summary?
The choice really hinges on 3 questions. What are you trying to see? How big is your sample? And how much access do you have?
Let's go through them.
Neutrons, ideal for both samples, finding light atoms like hydrogen or oxygen, or figuring out complex magnetic structures. It probes the nucleus and magnetic moment. The drawback is you need these immense, costly, competitive national facilities.
Electrons.
Mm-hmm.
This is the tool for the nanoscale and ultra-high resolution. Perfect for local analysis, imaging defects, and confirming 3D symmetry with CBED. It probes the atom's charge very strongly. The drawback is you need extremely thin samples and complex dynamic diffraction theory. You're mostly looking at surfaces.
And synchrotron X-rays, the ultimate high-flux, high-resolution electromagnetic source. It probes the electron cloud, but that tunability allows for specialized experiments like anomalous scattering to enhance contrast, solving problems similar to neutrons. Ideal for kinetics. The drawback is still high cost and high demand, though maybe more accessible than a dedicated neutron reactor.
And just to reinforce the core physics concepts that were described mathematically in the chapter. First, the fundamental link is the de Broglie relation. Lambda equals hmv. It established that all particles have a wavelength, which allows them to act as waves for diffraction.
Second, for electrons, we had to account for speed. The relativistic wavelength formula was necessary because at those high voltages, the electrons move so fast their apparent mass increases, giving them a much shorter, more useful wavelength.
And third, the massive contrast difference. The nuclear scattering length for neutrons is point-like and angle-independent, but its non-smooth isotope-dependent variation is fundamentally different from the X-ray scattering factor, which is based on electron density and decreases with angle.
That's a perfect summary of the core physics.
This has been an incredible deep dive into techniques that really define the cutting edge of materials characterization. Thank you for providing this detailed material and trusting us to unpack it.
My pleasure.
It's a crucial perspective shift, isn't it? The success of any advanced experiment depends entirely on picking the right probe to interact with the target structure.
And as a final provocative thought for you to consider, based on what we just covered, given the extreme difference in penetration depth, electrons are stopped by hundreds of nanometers, while X-rays and neutrons can go through centimeters, and given that electron scattering requires that complex dynamic theory, what are the practical implications for quality control in critical industries? If a defect were hidden deep inside the bulk material of a large engine component, which of these specialized techniques, neutron diffraction or synchrotron X-ray diffraction, would you prioritize for its analysis, and why would your choice between the two depend on the nature of the defect itself? That's something to mull over as you continue your study of atomic structure.
Until next time, keep digging deep.